Hi everybody, welcome to the Manifold channel. Today we're going to take a look at how to create custom filters in the free Manifold viewer. This is free software. You can download it and run it for however long as you like. It doesn't cost anything. There's no adware, no nagware, none of that. Just run it. It's free software. And what's cool about this is that all the filters that we create here will actually run GPU accelerated. The particular machine that we're using here is a AMD FX 8-core processor machine with a GeForce GTX 1060 card in it. That's a middle-of-the-road card. It's not a particularly hot card for gaming, but it does provide 1,280 cores. Anyway, we're going to work with this image here, which is St. Peter's in Rome. It's the Vatican. This is the St. Peter's Cathedral, and here's the big square in front of St. Peter's. And if we take a look at what this is all about, it's in pseudo-Mercator projection that uses float 64 numbers. It's a single channel image. And what we're going to do is we're going to learn how to do custom matrices. Now this assumes that you know what a convolution matrix is, and how that works is that you take, say, a 3x3 or 5x5 or a 7x7 matrix, and that matrix has numbers in it, and by computing those numbers against the image pixel by pixel, you can transform it. Surprisingly, many effects, for example, like edge detection or sharpening or blurs or stuff like that, are created just by putting different numbers into the matrix. And the key function, we're going to do all this in SQL, the key function that we use here is a string JSON tile. And this is a manifold function which takes a bunch of numbers here which define a matrix, and it creates a filter matrix. And that filter matrix can then be used in the convolution matrix process. It can be difficult to read what these numbers mean here as a matrix in line, so we can reformat them as I've done here. SQL allows you to mess around with white space however you like, and what I've simply done is just put in an extra carriage return in places like that to format this so you can see how the numbers are located. They're the first three numbers in the matrix, then the second three numbers in the matrix, then the third three numbers in the matrix. So you can see how that matrix is here in terms of numbers. When you go to websites on the web that tell you, okay, here's a filter to use for, say, Laplacian edge detection or something like that, and it gives you these numbers, this is where they go. To see what this thing here means, we can look at the template for the string JSON file, and what it does, the first argument, which we see right here, is a JSON string that gives you the numbers for the matrix. The second two numbers, this 3 and 3, are the x and the y dimensions of the matrix. In this case, it's a 3x3 matrix, so those numbers are both 3. This one is the number of channels that's in the matrix, and there's only one channel in the matrix, that is, it's only one layer deep. And the last is what to do if it's working against an image where there's the wrong number of pixels for this matrix to align, to give it a null or not. And we use true for strict. Now, how you actually use these to apply these to an image, use the tile filter function. What the tile filter function does is it takes this filter, which is created by this function here, and it applies it to tiles over and over in the image, given the radius of action. The radius of action for a 3x3 matrix is 1. So the way we'd actually use tile filter is like this. So that's a lot to unpack, I understand, but let's try to put it together and show how this works in reality. We've created a filter, and this particular filter here is for embossing. It's not one of the ones that's built into Manifold. It's an emboss filter. And we've put that inside the tile filter function so to tell it to, for whatever is the tile in the image, apply this filter to it with a radius of 1. So let's copy that. Control-C to copy. Go here to the St. Peter's grayscale image, and then here in the contents pane, I'll choose the transform panel. And instead of using one of these canned transforms, we're going to use an expression here, and I'll paste, control, right-click and paste. And there, we see the emboss in action. I'm going to turn that off for a moment to zoom in here a little bit farther. And Manifold is so fast that Manifold will actually preview the output of these convolution filters. The tile filter function is applying that emboss matrix that we created, and it's creating this emboss function. But what's with this grid? Well, what's happening is that if you're familiar with matrix convolution, you know that the matrices don't come right up to the edge of the filter, because right up to the edge of the image, because when you're right at the edge of the image, there's nothing else to go on for any particular tile. So in the tile region, there's going to be at least a 1 pixel width where there's no computation. So we need to fix that. And what kind of expression could we use rather than this expression to fix it? I mean, if you know Manifold, you know there's all sorts of tile border and stuff like that functions that could be used for paste that again, that can be used to trim this, but how are those used? Well, I don't know about you, but I find it very difficult to remember how to use these functions, and so I like to copy and paste from somebody that does it for me. And the best way to do that for something like Manifold is to go here into the contents pane, and here in the template, let's choose one of these transforms. Let's say blur, which also uses tile filter with a radius of 1. And what I'll do is I'll click the edit query button here. And what Manifold will do is it'll write the SQL that's behind that blur function. It'll open it in the command window. So I'll click edit query, and there, that's the SQL. So whenever Manifold actually runs that blur transform, this is what it's doing. And the way the blur transform works is that it takes the image that we're looking at, the St. Peter's image, and applies the blur, and it saves it into a new image. So if we take a look at that command that was written here, we can see how all this was done. And here's where all the, as they say, inside baseball happens. I'm going to add an extra carriage turn here to make the stuff more readable. What we're doing is we're using the tile filter function here, which applies to the results of the tile cut border function. And that tile cut border function eventually uses this filter here as a built-in part of it. That's the tile filter blur filter. The tile filter def blur function creates the matrix that's used for the filter, and that's applied with all this other stuff to cut borders and remove borders in this context. Now, what we could do is if we replace this filter here with the one that we created here in the example fragment, let's take this filter here. This is the function that creates the filter for embossing. What we could do is we could come here into the command pane and highlight this and click paste. And now what this should do is it should generate the image that is an embossed image. It's still going to call it blur because that's how this transform is set up. But let's run it and see what happens. We'll click the run button. And the result here in the project is an image called St. Peter's Grayscale Tile Blur Image. Double click it open and we see it is indeed the embossed image. Because what we did is we replaced the function that creates the blur matrix with the JSON filter, the JSON function that creates an emboss filter. Let's get rid of these two. And now let's think about how we can customize that. Now, in theory, you could just take this and replace these particular numbers with whatever convolution matrix filter you want. And there's hundreds of them that are published on the web for various things: Laplacians, Gaussians, all kinds of stuff for edge detection and all the rest. But it would be really kind of, I think, better if we could kind of compartmentalize this a little bit. And the first step to compartmentalizing is to use Manifold's ability to assign values and to use the values here. It's kind of like and we see that here in a query that I've written called custom filter. What we've done is we've replaced the function call down here with the @filter use of the variable that's defined. And up here at the beginning, we've defined this as a variable. So when we run this is going to create an emboss. And what I've also done is I've gone into here into the command filter, and I've changed the names around. So I've just done a Control H, and everywhere it said blur, I've replaced that with custom. And let's click replace, and 1, 2, 3, 4, 5, and I think that's it, 6. So now if I actually run this, remember we put the emboss filter here, it's going to generate an image called custom. And there it is. It's just named a little bit differently. That's a convenient way to, let's get rid of this, the ones we just created. And I'm going to look here at the custom filter. What I've done here is I've compartmentalized this here. I'm using this like a variable @filter, and here's where it's defined. So it's just more convenient to define the thing up at the top here, and we can search and we can just replace this with pretty much any filter that we want. So that's one way of doing this in terms of compartmentalizing this and making it simpler. A different way of doing this, if we take a look here at what the blur did, right here there was let's get rid of this, and let's once again create that blur from the beginning. Add a query. If you look at how this thing works, you can see that it uses this tildef blur function right here. What I'd like to do is I'd like to compartmentalize this, so instead of using this hard-coded, we're going to use it as we're going to have a function, and then we're going to have a call to the function. Here's the functionalized blur query. What we've done here is instead of calling the tile blur function, what we've done is we now have a thing called process tile. And here's the definition of the process tile function right here. It takes a function. In this case, we're using tile filter def blur, and that's embedded inside the function. And that function is in turn the one embedded between the tile remove border and the tile cut border. Now, why did we do that? Because what we'd like to do is we'd like to take it to one more level of compartmentalization, where we define what the filter is we use in one variable, and we use it inside the function here, so we can use it here. Let's click here into this query that I've written here, which does that. What it does, it uses a function, and we pass an argument to the function that's here. That's the filter that we want to use. So the function is basically tile filter using whatever filter we want. And the filters could be any one of these that are defined up here. I have a whole lot of filters here that I've defined. Here's the emboss one. Here's vertical edge detection, single style Syllable. Here's the Frey-Chen variant of single Syllable. And the way this works is that you can simply uncomment one of these. And by the way, you can download this project and use it, so you don't have to retype all this stuff. I mean, it's a lot more convenient. This is the isotropic edge detect Frey-Chen variant of the single Syllable matrix. It's a mouthful, but here's the filter, and I've just uncommented it. So now when this thing runs, when this query runs, this function, when it's called using that filter as an argument, is going to pass it to the tile filter function to do its magic. And all that is going to be embedded within the tile cut border and the tile remove border, so it all works correctly. And here we see the process tile is using that filter as the argument. Let's run this and see what it does. It's going to create an image called custom. And here in the project we see it did. And that's what the Frey-Chen filter does. If we take a look at it, it creates yet a different sort of edge detection using that particular algorithm. If you like, if you want to use your own filters here, this is actually a perfectly usable query. You can here we go, custom filter examples. Just open this one up and define yet another one here the way you like it. Of course, uncomment it. Here's an edge detect matrix. Here's a Laplacian edge detect, and so forth. So just define it using this as a filter. Oops. Define it using this value filter. Put it. Okay, let's try that again. Define it here in the list of parameters for the matrix, and you have your own custom filter. Now, why did we go to the effort of using a function? The reason why we went to the effort of using a function is so that we could compartmentalize everything that happens between the cutting the border and removing the border in this function. So we can change this to be whatever we want it to be. So let's say, for example, we want to do something complicated like a syllable filter, which isn't just a simple one tile filter expression, but it is a complex expression. Here's what a syllable filter looks like. We've defined not one but two filters. Here's filter 1, and it uses this particular matrix, and here's filter 2 that uses this particular matrix. And down here we have adjusted the process tile function so that it takes two arguments for filters, F1 and F2. And what this new process tile function does is it takes the tile filter applied to the first filter, squares that, takes tile filter applied with the second filter, squares that, adds the two results together, and then takes the square root of that. That's the so-called Syllable filter. And then down here we have adjusted it so that the process tile call takes two arguments for filter 1 and filter 2. So when this expression fires, filter 1 and filter 2 get passed to this function, and this function, you know, runs tile filter using the first filter, squares it, runs tile filter on the second function, squares it, adds the two together, and takes the square root, and that's the result. And we've taken the we've also replaced the names of all the images here, replacing custom with Syllable. So it's going to create something called Syllable image. When we run this, it automatically runs, and that's the result. That's the result of a so-called Syllable edge detection filter. That's, instead of using just one matrix, it uses a more complex expression. Now, by the way, all this, when it runs, automatically runs fully GPU. Why is that? That's because the tile filter function here that we're using here automatically applies GPU parallel processing. So it's going to fire all 1,280 GPU cores to make this calculation for us, which is pretty cool. We can do whatever custom filter we want, and it's still going to work. There's a variety of other filters you can do. For example, you can copy the syllable filter thing, paste it as a new query, and save it under the name of pre-wit filter. This is what a pre-wit filter looks like. It's a very similar processing function in that it's the square of the first and plus the square of the second one. Take the square root of that. But it uses different matrices than the Syllable. A more complicated multi-stage, multi-step filter than either the Syllable or the pre-wit would be here the Kirsch filter. The Kirsch filter is a very complex filter in that it uses 1, 2, 3, 4, 5, 6, 7, 8 filters. So here are all the filter definitions. It detects edges in each of 45-degree angles, each of 45-degree angles. Then it finds the maximum between us. So we have 8 filter values that we use here. The function we have adjusted so that the function takes 8 filter arguments. And what it does, it takes the pairwise comparison, the maximum of these two tiles, then the maximum of those two tiles, then it takes the maximum of those. Then it does likewise for these 4 tiles, then takes the maximum of both of those, then finally takes the maximum of all that. So the result is that it finds the maximum of any one of these filters and any one of these for each pixel. And the end result, I'm going to run it, is to find edges detected in any which way, basically. And that gets kind of busy, but if that's what you want with the Kirsch filter, that's what you get. Now, if we want to rename all this, if we want to use other image files, for example, notice these are all hardwired the name of the St. Peter's grayscale. What do you call it? The file here. We can change that by, again, Control H here, and St. Peter's grayscale, and replace that with, say, Ginevra. And just do that throughout the image. Close. And if we do that, that gives us this thing right here, which is the Ginevra filters query, where we replaced all the names so that it uses the correct image. And the image that we use is this one right here, the Ginevra grayscale image. That's Ginevra da Vinci, which is a work by Leonardo da Vinci that hangs in the National Gallery of Art in Washington, D.C. And let's delete that. Now, when we do this query, we also have to remember to adjust the size of the image, the property, because here we're creating an image. This is something, remember, that we copied and pasted from the original blur query that we grabbed. And to find out where these magic numbers come from for the rect, we can right-click on the image, click Properties, and there they are. So now when we run this, we're going to wipe out this poor lady here by doing a convolution matrix on her to find edges, and that's the result. You might think, okay, that's a pretty crazy thing to do, but there's reasons for doing nutty stuff like that. For example, if we take the original image and we put it above there, and now let's change the transparency to 80%. We can see that the result doing edge detection has highlighted places where there's cracking in the paint. And if you're an art person, you may be interested in seeing that kind of stuff. If you're not, if you're into geographic and analytics, it'll reveal edges in all dimensions, as we saw with the St. Peter's image. Well, that's been a very long video. It's 20 minutes. Apologize for the great length, but I hope you've enjoyed it. I hope you've seen how easy it is to do custom filters. Manifold, of course, is steadily adding all the popular filters to the transform pane, more and more and more and more of them. But there's no need for Manifold to wait. No need to wait for Manifold. If you want to add custom filters, you can use these as kind of a template and kind of roll your own for anything that you see on internet or read in a book on convolution matrix filters. They're right here. This is set up for 3x3 filters. A fairly simple adjustment allows you to do 5x5 or 7x7 filters. And you can always even do more custom filters, like we saw how to do the Kirsch and the Syllable filters. Thanks for watching, and goodbye from Manifold Land. Well, that was fun. If you want to see more, visit us at www.manifold.net. As always, Manifold delivers the world's most advanced, highest quality spatial products for GIS and DBMS at a low price that you can afford. Once again, that's manifold.net. See you soon.